In this video, I'll continue my lecture on isomorphic graphs. In particular, I'm going to talk about how do we know when two graphs are not isomorphic. So remember, an isomorphism between two graphs means that it's a bijective function that preserves edges. So here's two graphs from our text, F1 and F2. And I just want to point out a way to see that these two graphs are not isomorphic. So one thing I've done here with these two graphs, they might look, I don't know, similar. Maybe it's conceivable that I could rearrange these vertices and make them look like these, but I'll show you why it's not. So one thing I've done with this is I've listed out, I've included the degrees of the vertices in the graphs. I've just listed out the degrees of the vertices. Remember, if we have an isomorphism, that needs to preserve edges. And so in particular, if I have a vertex of degree 2, or maybe I'll go back to this example, here I had a vertex of degree 3 that in order for my isomorphism to preserve edges, this needed to be sent to a vertex of degree 3 in the codomain graph. So that is, phi needs to preserve degrees of vertices. So here I've listed out the degrees of the vertices, and one thing I'll notice is that this vertex here has degree 5. So that means whatever I send to this vertex here has to have degree 5 in F1. But if I take a quick look at the vertices of F1, 2, 3, 4, which I've done, there is no vertex of degree 5 here. And so there's nothing I can send to this vertex that's going to preserve edges. So degrees aren't preserved. Some other really basic things is, if my two graphs don't have, so we can say, all right, sorry, let me back up, degrees aren't preserved, so F1 is not isomorphic to F2. There's no isomorphism I could give here. That's one way you can tell. There's a couple other easy conditions for us to tell if two graphs are not isomorphic. In particular, since phi, the isomorphism is a bijection, if we had an isomorphism, it would be a bijection, which means that the size of the number of vertices in F1 would have to be the number of vertices in F2. That's true here, but if we had a situation with two graphs with different number of vertices, they wouldn't be able to be isomorphic, because then there wouldn't be a bijection between the two. The next thing to note is that since an isomorphism preserves edges, the number of edges has to be the same in both graphs. So that is, the size has to be the same. So that's three easy conditions for us to tell if two graphs are isomorphic, then these three conditions have to hold. They have the same order. That is, G and H have the same order. They have the same size. They have the same number of edges. And three, this point I made with F1 and F2, the degrees of G are the same as the degrees of H. Or I should say degrees of vertices of H. And again, same order follows from it being a bijection, same size follows from the isomorphism preserving edges, and this degree thing again follows from the bijection preserving edges again. So these three things have to be true if they're isomorphic. And again, this tells me if I look at the contrapositive of this. So remember, if I have a implication, so some statement implies some other statement like I do here, P being if two graphs G and H are isomorphic, that's my hypothesis. Q being my conclusion, then they have the same order and they have the same size and the degrees of the vertices. These are all and statements, conjunction here between these statements. So Q here would be same order and same size and the degrees of the vertices are the same. The contrapositive is equivalent. So even in logic, we have a sense of same, and that means the truth values are the same for all possible inputs into the statements. The contrapositive has the same truth value It's equivalent to the original implication, and it's not Q implies not P. So what that means here is that if two graphs, G and H, do not have the same order or do not have the same size, or the degrees are different, I'll just say that, degrees are not the same. So that's my not Q. See how I've negated this conjunction, these and statements, they're now ors. If either one of these conditions isn't satisfied, then we can say for sure that G and H are not isomorphic. Then G is not isomorphic to H. So that's how we can use, this is theorem 1.6 from our text, to show us when two graphs are not isomorphic. But this is just three conditions that have to be true for two graphs to be, when two graphs are isomorphic. There's a lot of other things that have to be true. In general, isomorphism preserves graph structure, and there's more to graph structure than just order, size, and list of degrees. So let's take a look at two other graphs. So that is, this isn't the only condition. I could have two graphs having the same order, the same size, and the degrees are all the same, and the two graphs are not isomorphic. Right? That is, the converse of this is not true. So let me make that note. Converse is not true in general. So let me look at an example. Let me get two other graphs here. They're going to be non-isomorphic, and yet all of those three conditions are going to be satisfied. Let me redraw that edge. And then I'll draw another graph over here. This is what's called a prism, and this is what's called a complete bipartite graph. So I just want to see, are these two graphs the same? Is there any way I can rearrange the vertices here and make it look like this? Can I find an isomorphism from one graph to the other? So one thing I'm going to do is I'm going to label with degrees of vertices. So it looks like every vertex in this graph has degree 3. Every vertex in this graph also has degree 3. So the degrees are all the same. The orders are the same. Order 6. Order 6. Since they have the same order and all the degrees are the same by the first theorem of graph theory, right, theorem 1.4, the sizes are also the same. In particular, they both have size 9. So these two graphs meet the conditions that they have the same order, same size, and same list of degrees, yet these are not isomorphic. So this is what I mean by the converse of that theorem not being true. So why aren't these two graphs isomorphic? We have to come up with some reason why we shouldn't be able to find an isomorphism between them. So one thing I can think about here is lengths of cycles, or just existence of cycles in graphs. So in particular, I have these three vertices down here that are all mutually adjacent. That is, this graph has a K3 in it as a subgraph. So it has this triangle in it. If I look over here, there are no three vertices that are mutually adjacent. So let me maybe highlight that. So these vertices are mutually adjacent. And there are no three vertices are mutually adjacent over here. So this idea of having three mutually adjacent vertices or having k mutually adjacent vertices. This is a structural property of the graph. And that means it's preserved by isomorphism. So why is it preserved by isomorphisms? If these three vertices are mutually adjacent, and I'm trying to find a bijective function over here, since that bijective function has to preserve edges, that isomorphism has to preserve edges, that means these three vertices that are mutually adjacent over here have to be mutually adjacent over here. Since this doesn't have any three mutually adjacent vertices, there's nothing for this group of three to be sent to. So there's no isomorphism that can exist between these two graphs. Again, this is not the only property, right? So you might think, oh, well, can we just add this to our list? Could we extend theorem 1.6 and also add that they have the same number of k mutually adjacent vertices, something like this, or they have the same number of triangles in them, something like that. We could totally extend theorem 1.6 to say that. But again, the converse wouldn't be true. Just because we guarantee the existence of mutually adjacent vertices, three mutually adjacent vertices or k mutually adjacent vertices, that's not going to be enough for the converse to be true. We haven't made the theorem strong enough in order for it to be true. And you might add, well, are there other properties that we could add to theorem 1.6? Is there some bigger theorem with a complete list of properties whose converse holds? So we just have to check these, I don't know, 10, 12, 100 properties to guarantee that two graphs are isomorphic. And the answer is no. There is no complete list of structural properties of a graph. There is no sort of huge theorem that just gives us a list of properties that is whose converse is also true. And so that kind of just shows you the sort of variety in the structure of graphs. There's no big complete list of properties that guarantees isomorphism. So in general, it's actually a kind of hard problem to see when two graphs are isomorphic or not. And in fact, computationally, it is a hard problem. This is known as the graph isomorphism problem. You can look it up. It's a difficult problem for computer scientists. There is no known efficient algorithm for doing this that runs in polynomial time. So there's a couple other examples in this section you should definitely take a look at if you haven't yet. In particular, there's an example where we do have two graphs that have same order, same size, same list of degrees, and they have the same number of triangles in them, but also aren't isomorphic. And so you can take a look and see how that's proven in our book to show that those are non-isomorphic. Okay, that's it for this one. I'll see you later.